thank you, Peter, for kind words. And I have to admit that when I came up with this, or after I came up with this title for the presentation, I realized that I had dug myself into a hole. Because how I see it is that I'm thinking, what is there not to care about sea ice and its failure, basically. And I mean, now I guess that my job here is to try to make you basically think the same way that I do. And I could be talking to you about the fact that up to about 15% of world's oceans are annually frozen during some point of the year. And then I could be talking to you about climate change. I could be talking to you about the fact that probably everybody in this room has been following news about the loss of Arctic ice and so on. And I will try to get back to that as well, or sort of touch that topic as well a little bit towards the end of my presentation, but I mean that's something also that is closely related to sea ice deformation and sea ice failure. So when I started to think about this question, then I think that the first thing that I had to think about really was that why do I care about sea ice deformation, sea ice failure? And this is a picture from Baltic Sea from 2016. I'm on board of research vessel Aranda. And once you have been in field, once you have seen sea ice in nature in these kind of conditions, it's very difficult to not care about it, basically. It's quite, I mean, majestic in one word. This picture, by the way, is staged. That's not me. I hate cold, in fact, and I would never go outside in these kind of conditions without proper gear. But anyhow, so if you look on this picture, what you see basically is sea ice and how it is often in Baltic, for example, or any other area that is away from the coast. It's deformed, it has failed, and what you see basically there always is that you hardly have no level ice, but you have all kinds of formations that you see out there. And those formations are often something like this. So this is an ice ridge, ice that has failed into a big pile of blocks, ice blocks. It's not uncommon to find these ice ridges that are about 12, 15 meters deep in the Baltic Sea. I think that the record is something like 30 meters. But if even an average size ridge can be a size of an apartment building, basically. It's a result of ice failure process, basically. That was actually something that I started to work on when I started to work on ice, and these are pictures from I think 2009, 2007, when I started to work on something that I call numerical ice mechanics, and that is actually sort of sometimes I feel sorry for the sea ice in a way that it's actually this numerical mechanics and computational mechanics that was my first love and kind of brought me into actually studying problems related to sea ice. So what I modeled here was actually those ice ridges that you just saw on the previous slide and how they deform and how those ice ridges then fail. It's a material experiment on an ice ridge material properties, basically. So, I mean, this is how I find ice failure fascinating. And then I started thinking, okay, that what could be then something that would be interesting for you. And I started to, where I wanted to start basically is that I bring things now close to home, close to Aalto, basically. And I start to talk about green transition and Baltic Sea. So if we first look into this map, what you see there basically are, at least as of yesterday or Sunday, all the developments or all the plans for offshore wind farms on the Baltic Sea. All these different colored polygons here are basically plans for wind farms. And now you probably guess where this is going. So basically, the challenge with these wind farms is that they will be built on areas that have sea ice. And this is something totally new. I mean, hasn't been done anywhere else before. And it's, of course, you know, a result of, again, climate change. It's a result of you know, us wanting to produce green energy. If I remember right, basically the wind energy potential of the Baltic Sea, I mean the whole Baltic Sea, not only the areas that freeze, is something around 90 gigawatts. And that translates to about 5,000 big wind turbines that need to be built and need to be then maintained and so on. And of course, you know, the norther you go, the more serious the ice conditions come and more, you know, challenging conditions you are going to be building all these. So there are a few of these that have been built in icy waters. Oh, there's 11 of them, close by Pori. They are close to coast. I don't think that they've been built into especially very hard ice conditions and so on. But some of them have been built. And well, they're at the moment built very, very robust. Like they will, it's safe. They will not fail. But they are not economical. They are not, you know, in a way sustainable. That you could do a better job in building these there. I mean, there's of course, you know, when people start to do this, there's a lot of you know, knowledge from oil industry and things like this on how to build things on ice. Well, people who were building offshore structures related to oil and so on, they did not really ever have to think about optimizing those structures too much. You know, you just needed to make sure that okay, nothing fails, because that would have been a total catastrophe. Well, luckily, no one is seriously planning to build anything oil related really on the sea in Arctic seas anymore. But the knowledge that relates to these kind of structures comes from there. Well, these kind of structures are a little bit different from the structures related to oil. So what you have is a slender structure that has a lot of mass on top of it. And now you have at the waterline there an ice load acting on that structure. And what the result is, if you just go with this kind of cylindrical, you know, standard solution for an offshore wind turbine, which probably is in our mind when we think of offshore wind turbines, you're going to run into situations where you are going to have ice-induced vibrations. So basically those structures are going to start shaking, they vibrate, they go through fatigue, they might even break and so on. So it's a situation that you don't want to end up with. And that's something that especially my colleagues in TU Delft in Holland have studied. I mean, when we study these kind of phenomena, it's sort of a totally new type of structures. You don't have them yet in full scale, but what you can do then is to take everything in model scale. And that's what we have been doing in Aalto Ice Tank. And this is really, I mean, it's a collaboration with TU Delft. It's not, you know, by no means just my work there and so on. But it is, you know, worth mentioning, I think, that the experiments that were done in the tank, I mean, our people working at the tank were developing ice where you could actually then test structures in model scale that could then go through ice-induced vibration in a controlled manner. That's the first time that it's been done in any model scale facility. Well, but I mean, okay, so this standard solution clearly has its challenges. So what do you do then? I mean, one way of avoiding these kind of ice-induced vibration situations, maybe, we don't know yet if it's possible totally, is to start equipping these structures with something that are called ice cones. So what happens then is that basically ice is forced to, you know, kind of be pushed out of a plane, and it's forced to fail by bending. And that is now supposed to help us in cases where, you know, you would otherwise get these ice-induced vibrations, but basically by changing the failure mechanism there, you don't, ice failure mechanism there, then you don't run into these kind of troubles, maybe. But of course, I mean, if you then think back to what I said earlier related to these ice ridges and so on, so what you here effectively do on the same time is that then you basically expose these structures, or you make them bigger, and you get bigger forces from these ice ridges and so on. So it's not, I mean, optimal solution either. What I've done quite a bit, and what we are currently then doing is, again, because we don't have these structures exactly, we have to test them in our tank, or we can run numerical models on it. And really the idea here is then, again, look into ice failure, look how it fails against the structure, and look into the loads on these offshore wind turbines, based on that. And now, of course, then, you might ask that, okay, it's a sort of a interesting engineering problem that has direct impact someday when these things are actually built in massive amounts and so on, that we know how to optimize, each of these turbines maybe for given kind of ice conditions and so on. Okay. But there are more challenges, okay? So when you start to look on the wind turbines, so they don't come just as, one wind turbine, but you have to build a farm in order to anything make sense, basically, economy-wise. And when you build these, they are going to be there for 20, 30, 50 years maybe. And then you have to start asking questions related to basically how the sea ice will be in the future. And this is then more complicated topic. So basically what you are having is climate change induced effects on sea ice itself, sea ice properties. You're going to have more drift ice, more ice moving around. You are going to have maybe thinner ice, maybe softer ice. It's difficult to say. And it's even more difficult to say how the mechanical properties of that kind of ice, when it comes to ice structure interaction, basically are affected. Now, then of course the challenge here, as you see in this simulation as well, is that when you start to build these structures close to each other, they're actually interacting. And they are basically breaking, ice in a different way than a single turbine would. And I mean, then if you start to build these offshore wind farms into, again, in the icy conditions, which again, I mean, what are already really complex. So basically, if you look on how the sea ice in in this picture, for example, behaves, this is also from Baltic Sea. I think Åland is over here and Turku is somewhere over here. What you see here is actually a very complex system made out of ice flows which interact, form these ridges and so on, and form these interesting looking complicated fracture patterns and so on. And now you go ahead and basically put these wind farms there. So what you are going to do there is, well, actually I don't know what is going to happen, but what you are going to anyways create there most likely is that you're going to change the dynamics of these sea areas. I mean, it's a really vast area basically that these things are going to be taking from the sea. And it's an interesting problem in a way, that what we have been now doing during the past couple of years is to actually look into this kind of ensemble behavior of offshore wind turbines in these kind of areas. Or let's say that we are heading strongly to that direction. And I mean, people have really woken up to this situation in a way. You are running out of space on Baltic Sea pretty much soon. So that also has then affected our modeling, basically, or the type of modeling that I do with my group. And sort of the trend, I would say, that has been here, that I really started modeling these engineering scale problems, single ice ridges and so on. I modeled in the past also, ice in a scale of just millimeters or centimeters and so on. And where we are now going is that we are modeling ice in scales that are approaching, scales of parts of Baltic Sea and so on, which then leads us to the next steps where we are actually looking in the direction of geophysicists studying on very large scale ice dynamics problems like the Arctic ice pack and they are looking into our direction on how we can actually help them in understanding how this Arctic ice pack then behaves. And I think that basically ends my presentation. So, thank you, everyone.